Introduction to Complex Numbers. As we talked about in the previous lecture, a complex number is made up of real numbers and imaginary numbers. The real number is the type of number we use every day, the counting numbers, 1, 8, 22, -4. The imaginary number is any derivative of the square root of -1. And remember, we technically cannot get a square root of -1 because -1 times -1 equals 1. So we cannot derive a -1. But as I said, as we look at some things such as atomic decay, extrapolation into before the beginning of a certain formula, we can go before 0 and look at this and project it backwards. So we call the square root of -1 I. And again, as I said yesterday, if I have the square root of -1 times the square root of -1, that actually, oops, put a negative there, that actually equals -1. And that also is -1 times -1 is square root of -1, sorry, times square root of -1 is I times I, which equals I squared. And I squared is equal to -1. This basic juncture tells us what we're going to be doing for the rest of this lecture. I've already built from this. Now, as I said in the previous thing, I squared is -1 because I times I is -1 because square root of -1 times square root of -1 is 1. Now, when we look at this, these are complex numbers here. This whole set right here, 3.6 plus 4i is complex. This is the real component, it's r. This is the imaginary component, 4i. Negative 0.02 plus 12i is another complex number. The 0.02 is real. 1.2i is the imaginary. 25 minus 0.3i. That is also a complex number. 25 is real. Negative 0.3i is the imaginary number. And then finally, I get 0 plus 2i. Well, this technically is just an imaginary number. It's just 2i. But if we want to get into semantics here, my real number is 0. So 0 plus my imaginary number, 2i. And when we simplify a complex number, and I take it a slow step by step because I do not want errors being made. I tend to make mistakes and I try to rush it. So, and I want to remind you, when we are trying to factor out roots, number 1, for square roots, that means there's a 2 there. And if I have the same base and the same factor, I can separate this out. For example, the square root of 9 times the square root of 5 equals the square root of 45. And conversely, let's look at the square root of, let's say, 243 equals, and these are both square roots. I know if there's nothing there, I know it's a 2, equals the square root of 81 times the square root of 3. And I can simplify this. And the square root of 81 is 9. I really can't do anything with square root of 3. So it's 9 square root of 3. Same as square root of 3. I'm just simplifying it. And I can separate it out. I have the same base, and both these are real numbers. So that's my same base. And then I've got the same root, and this is a 2 here. So negative 36, that's the same as negative square root of 36 plus square root of -1. Well, the square root of 36 is 6. And I'm renaming square root of 1i. So this square root of -36 is simply 6i. Square root of -27. Well, I can make that into three separate components. Square root of 9 times square root of 3, which is 27, times square root of negative 1, and there's my negative 27. Square root of 9 is 3. Again, I can't do anything square root of 3. And then square root of negative 1, I'm going to replace that with I. And that's on the outside of that square root, so that's why I put it over here. So negative square root of 27 is the same as 3I times square root of 3. Now here's what I want to be a little careful of. 8I times 3I. Well, 8 times 3 is 24. And I times I is I squared. But remember, I squared is negative 1. So this is the same as 24 times negative 1, which is negative 24. Now we talk about the complex plane. This is the same as the x and y coordinates in a Cartesian plane, except my x-axis is not called my x-axis anymore. It's my real axis, or my r. Positive r's go this way. Terrible plus sign. Sorry about that. And then negative r's go this way. And then my imaginary is where my y-axis is. My plus imaginaries go up that way. And my minus imaginaries go down that way. But for all practical purposes, we utilize it the same way as we do the Cartesian plane with an x and y coordinates. Now, we'll be using more of this in vectors in the coming weeks, but this is a good start for it. If I have a complex number, 3 plus 4i, right here, 3 plus 4i, that's 3 across the real axis, and then 4 up on the imaginary axis. 1, 2, 3, 4. And there it is right there, my little dot. 4 minus 2i. I'm going to go 1, 2, 3, 4 on my real axis. And then it says minus 2i, so I'm going to go down. Minus 1, minus 2i. And there it is right there. So instead of x and a y, we have a real and imaginary. And instead of a x comma y, it is real plus imaginary. Now let's, on the left here, it wants me to map 2 plus 2i. So I'm going to go, here is 2 right here. Go up 2i. So there it is right there. There is my 2 plus 2i. 2 plus 2i. And then the second one it wants to do is minus 3i. Minus 3 is on the left here. Here's minus 3i right here. So where the twain meet is minus 3, or maybe there, minus 3i. And then on the second one, negative 1 minus I. Here's negative 1 right here, minus I right here. Negative 1 minus, and that's actually 1i, but we just call it I. And then 0 minus 2i means there's no movement on the x-axis. We start at the origin and then down 2. So here's 0 minus 2i. 0 minus 2i. Now, figuring out distance on complex numbers on the complex plane is no different than the xy axis in the Cartesian plane. And what we're doing here is we're going to use the Pythagorean theorem. And there's going to be two questions here. Now, the first one on this slide is going to be, what is the distance between negative 5 minus I and 2 plus 3i? Well, we can use the Pythagorean theorem. I got 2 points here. Here's my first one, minus 5 minus I. Here's my second one, 2 plus 3i. And I can figure out what the distance is. And these are going to be absolute values here because we're still using the Pythagorean theorem. A squared plus b squared equals c squared. And on my x-axis, I go from negative 5 to 2. And the absolute distance is 1, 2, 3, 4, 5, 6, 7. So my absolute distance between -5 and 2 on the real axis is 7. And we'll call that my A, where a squared plus b squared equals z squared. So my A is 7, a squared is 49. And then my B is going to be my vertical distance, and that's on the imaginary plane. And it goes from -I right here to plus 3I, and that's 1, 2, 3, 4. So the absolute distance from -I to 3I is 4I, or 4. Now, and that's going to be my B, and 4 squared, B squared is 16. Now, earlier in class, I realized I made a mistake. A squared plus B squared is C squared. So it's 49 plus 16. And I put 61. That should be 65. So when I add 49 plus 16, that's 65. That's C squared. The square root of 65 is about 8.06. So my distance between -5 minus I and 2 plus 3I, which I'm drawing here right now, is 8.06. And we just use the Pythagorean theorem in the same components. Just remember, even though you're talking about an imaginary axis, imaginary numbers, you're still counting. Now we want to find the midpoint of these two. And this is actually even easier. If we know our 2 points on the horizontal side and 2 points on the vertical side, where they're located from, we can find the halfway mark. Well, on my horizontal, which is my real, like I said before, it's -5 plus 2. And what is the average halfway between those two? -5 plus 2 is -3. I'm going to divide by 2 because I'm going halfway across. And that means on the real axis, it's -1.5. So here's 2 goes to 1, goes to 0, -1, -1.5 right here. And 1.5, -1.5 to 3 is 4.5. And then from 5 to 1, I'm sorry, 3.5. And then from 1.5 to 5 is another 3.5. So this is in the middle, right on the real axis. Same thing with the imaginary axis. Oh boy, I'm drawing here. Let me erase this, making a bit of a mess. One I already used to make. All right. So I'm going to find a distance, and I already know it once. It goes from -I to 3I, and that is a distance of 4. But I got to find the halfway mark. So it'd be -1 plus 3 is -I plus 3I, which is 2. And divide in half. 2 by 2 is 1I. So my halfway mark at this point is right here. Here's 1I. And that's distance from there to there of 2 jumps, and distance from there to 2 jumps. So yeah, there is my imaginary coordinate. So the midpoint for -5 minus I and 2 plus 3I is going to be -1.5 plus I. Now, we use the word conjugate. The conjugate is basically the opposing imaginary coordinate. We keep the same real coordinate. For example, if I have 2 plus 3I, which is right here, the conjugate is 2 minus 3I. Same coordinate on the real axis, but we're going with the opposites on the y-axis. And we're going to see where we use this in real-life calculations in a moment here. As I said, what's interesting about this is when I add 2 plus 3I and the conjugate 2 minus 3I, notice I get double the original distance on the x-axis, or I say the real axis, and the y's cancel out. 2 plus 3I plus 2 minus 3I. 2 plus 2 is 4 right here, and then 3I minus 3I cancels out. And this is what happens with the conjugates. What's interesting, we'll be using this in vectors, is if I look at this right here, and I take this vector right there, and I moved it to right here, it gives me the same distance. Same thing here. If I took this right here and put it right here, it goes back to where it originally was. And this is the basis of vectors. We could tell real life where something starts and ends with the conjugate. Now, conjugate 3 minus 5 conjugate 3 minus 5i on the left plane. Well, here is looks like a 2 there. Should be 3. Let's see. Find a conjugate 3 minus 5 on the left Cartesian plane. So I'm going to find 3 minus 5i is right there. And let's change the color. There is 3 minus 5i. I'm going to find the conjugate for that. And I'll make it blue. So that'd be 3 plus 5i right there. And as a conjugate, 3 plus 5i. And I'm going to put equals conjugate. This is C equals conjugate. CON. Now, negative 5 plus I. And there is right here. I did this one right. Negative 5. Here's negative 5 right here. Plus I. Here's the original one. The conjugate of that is 3 minus I. Right there. So we're just looking across the real plane, but on the imaginary axis. Now we'll use this, especially with computer simulations, because in addition, not liking variables in their denominators when we go rational functions, which will be next week, we also don't like imaginary numbers. So what can we do? We can use the conjugate to get rid of those imaginary numbers, especially when you have detailed multiple rational functions. It can get real complicated real fast, and we want to make it as simple as possible. So let's move as quickly as possible. And here I've got a fractional equation, 1 plus 2i over 4 minus 5i. I do not like that imaginary component in the denominator. So it's 4 minus 5i. What's the conjugate of 4 minus 5i? 4 plus 5i. And as you know, anything over itself is 1. So I can multiply any fraction or anything by 1. I still get the same answer. X over x is 1. I over I is 1. I plus 2. If you want to get technical, over I plus 2 equals 1. Anything over itself is 1. So what I'm going to do is I'm going to multiply this 1 plus 2i times 4 minus 5i times the conjugate. 4 plus 5i in the numerator, 4 plus 5i in the denominator. As I said, this is equal to 1. I'm not really changing anything. But here's where it gets interesting. I'm going to do the denominator first. 4 minus 5i times 4 plus 5i. We do FOIL. 4 times 4 is 16. That's the first. Then do the outside. 4 times 5i is 20i. Then do the inside. Negative 5i times 4 is minus 20i. And then negative 5i times 5i is minus 25i squared. What's interesting is these two cancel out. This is the perfect square trinomial. That's really what, when we multiply the conjugate by its original complex number, happens. It cancels out. It is basically you're creating a x squared minus a squared. If you remember this, when we're doing factoring, and this is x plus a and x minus a times x minus a. So really what we've done here is we've canceled out these two, and now I've got 16 minus 25i squared. Remember, I squared is negative 1. So it's 16 minus 25 times negative 1, which is actually plus 25. Negative 25 times negative 1 is 25. So it's 16 plus 25, which is 41. So our denominator is no longer an imaginary number. It's 41. So we got to do the numerator. And we'll just use FOIL for this. 1 times 4 is 4. 1 times 5i is 5i. 2i inside 2i times 4 is 8i. And then I got 2i times 5i, and that should be not I squared, 10i squared. So it's 4 plus 13i, because 5i was a squared, minus 10i squared. And remember, this is the same. 10i squared is the same as negative 10 times negative 1. So this is actually, negative 10 times negative 1 is plus 10. So this is going to be not 3, but 10 plus 13i over 41. And we use the conjugate to get rid of that denominator with an imaginary number in it. Go one more here. Negative 6 plus 8i over negative 4 minus 3i. And that should be 3i, not 31, which I've done correct in the rest of them. The conjugate 4 minus 3i is minus 4 plus 3i right here. And the same as 1. So I'm just rearranging it. And when I multiply this out, let's do the denominator first. Negative 4 minus 3i times negative 4 plus 3i. It's a difference of squares. Negative 4 times negative 4 is 16. There's my negative 4 and my negative 4. That side, negative 4 times 3i is minus 12i. Negative 3i times negative 4 is plus 12i. And then negative 3i times negative plus 3i is minus 9i squared. Well, as I said, these two cancel each other out. So I'm left with 16 minus 9i squared, which is negative 1. So 16 minus 9 times negative 1 is actually 16 plus 9, which is 25, which is what I got right here. I got a number in my numerator, a real number. Now, let's do the numerator. Negative 6 times negative 4 is plus 24 in the numerator. Negative 6 times 3i is minus 18i. And then the inside, 8 times 8i times negative 4 is minus 32i. And then I've got 8i times 3i is 24i squared. All right, so I've got 8 minus 18i minus 32i is minus 50i. We'll leave that one alone. We got 24 down here. And then plus 24i squared is the same as is 24 times negative 1, because I squared is negative 1. So really all I've got here is 24 minus 24, because this becomes 24 minus 1 is minus 24. They cancel out. All I'm left is with 50i over 25. 25 goes into 50 2 times. So all I'm left with really is 2i.